Right. So we have a lot of applications that could benefit from schedule. But I can't, demonstrating that it was better. Kind of a marketing. Yeah. Also people really spend about $5 we developed our own. I'm still, it's a constant argument about. Introduce these topics. That's very interesting. Thank you. They just don't really get this. I found this. Where is that? Over here? Oh no, we have. We're there. Yeah. Top of the customer.
I think we have flexibility.
They're a big customer. Yeah. So it's in the city. There's not any. Yes.
Yeah, we need to ask for it. Okay. So what is she saying? Start. Okay, hello everyone. Welcome to the meeting of the 6LO working group. Please make sure that you are in the right room. My name is Carlos Gomez. This is Shweta Bandari, and our responsible AD is Suresh Krishnan. So first of all, we need volunteers. We need a JavaScribe. Is there anyone who would like to volunteer as a JavaScribe? Okay, let's move on for a while, but if anyone would like to volunteer, please do so. And we have Dominique, who volunteered as a minute taker. Thank you very much, Dominique. Is there anyone who would like to volunteer as a second minute taker? By the way, recall that the idea is taking notes of the main points of the discussions, the main outcomes, the main action points, but not everything that's being said. In any case, I understand that the minute-taking process will take place on the Etherpad, so feel free to join the Etherpad and contribute to the collaborative effort of minute-taking. So on the slide, you can find a number of pointers to relevant resources, which are the online agenda, the Java room, the Meet Echo, and the Etherpad. This is the Nodewell. Please make sure that you have read it. It contains a number of pointers to policies, IETF policies on important topics. So please make sure that you are familiar with it. And now let's go through the agenda for today. So the first slot is the usual chairs introduction that's currently in progress. The next slot is the presentation of the IPv6 over NFC document, basically the revisions after the ISG evaluation. Next, initially there was scheduled the presentation by Charlie about the deadline time draft, also the revisions after ISG evaluation. However, he will present this remotely, and he will do it at the end of the session because of some unexpected issues that have appeared. So unless there's any objection, the proposal would be to move Charlie's slot to the end of the session. After that, the next presentation will be given by Pascal. This will be a status report of the fragmentation drafts. And then there will be the presentation of the status report and next steps for the applicability and use cases document by Young-Jung. Then there will be a set of 2 presentations that are related with neighbor discovery that will be given by Pascal, starting actually by the second one. So it's not the same order that's shown here, if there's no objection. So the first will be the proposed maintenance scheme for RFC 8505, and next there will be the unicast lookup. And by the way, since we have some available time, unless there's any objection, the slot for the unicast lookup would also be of 15 minutes. Finally, there will be the presentation of new work, which is a new method for header compression given by Brian, and the related document is entitled Asymmetric IPv6 for IoT Networks. And as I said before, actually the last slot will be the one by Charlie, unless there's any problem. So is there any comment on the agenda considering these proposed changes? Okay, thank you. So now let's go through a status report of the working group documents. We have 2 documents that have been evaluated by the ISG. These are the IPv6 over NFC and the deadline time documents. There was a number of outstanding discussed positions on both, and both documents were updated before the cutoff date. And the next step will be seeing whether the updates are sufficient to satisfactorily address the comments that were made. You can see on the slide a summary of the ISG ballots as they are today. And there was another document that was submitted to the ISG, however, it hasn't been yet evaluated by the ISG, which is the address protected neighbor discovery draft. Then there's a set of 4 other documents that passed working group last call. The first 2 are the documents that are related with fragmentation, and these are the 6LoWPAN fragment forwarding and the fragment recovery documents. For this, the Shepherd review has been done, and both documents have been updated. In fact, this morning there has been the publication of the new revisions, and the comments that were given by the Shepherd are addressed by the new updates. Then there are 2 other documents that passed working group last call. One is the IPv6 Badman Router. For this, we requested a review from Sixman, and actually this morning, one reviewer from Sixman agreed to do this review and provide the review in 3-4 weeks. And the other document is IPv6 mesh over BLE links, for which a Shepherd was assigned, and the next step will be getting the Shepherd review and write-up. Then there are 2 other working group documents that have not been updated since Prague. The first is the 6LO applicability and use cases draft. As you may recall, there was a working group last call held for this document, which, however, ended without feedback. So today there will be some time for discussion of the current status and next steps for this document. And finally, the last working group document is IPv6 over PLC, which as you may recall, was adopted as a working group document before Prague, and however has not been updated since then. So perhaps, is there any author of this document that would like to express anything on the mic about current status and next steps? Yeah, it's over there.
Okay, Remy Liu from Huawei. I'm one of the authors of the IPv6 over PLC. So before this meeting, we have not got a chance to update the draft. So we will update the draft just after this IETF meeting, and we will come to the mailing list for the comments. Okay, thank you.
Okay, thank you very much. So is there any comment on this presentation? Okay, then we can move to the next slot, which will be the presentation of IPv6 over NFC, basically the report of the revisions after the ISG evaluation.
Yeah, this is about the draft, the number 14 and 15. Actually, I proposed two documents. Okay, this is every time I show you the quick introduction about the NFC. And this one is the history and status of my draft. Actually, there was the IGSE reviews on March. I have a lot of feedback and discussion. And then I produced the 14 and 15 draft version for this meeting. I will give you some quick introduction of the review with the 5 slides. The first one is marketing inspection. Actually, there was something marketing stuff on my draft. Something inspection is not really good. So I just reword all of them with the only technical keyword and point, and some others are not relevant keyword is removed. The chairman, the comments and the strategy helped me about. Thank you too. And another one is the editorial changes, usually of a whole document, and because of some typos and the syntax. And RFC 2119, actually there's a lot of may and some shoe something. I just removed all the may and I changed this one something to must, something like that. Thanks. And the next one is about section 3.4. This is about MTU and the example of the extension option. Actually, there was some review about what is the MIU. Actually, this is actually the same as MTU in the NFC site. So I just put the MTU in the front of the equation, and I revised for the figure number 2, the full clarification, like that. Next one is the section 4.1 about the figure 3. Actually, this figure is actually some part. Actually, the physical and link layer is redundant to the figure number 2. So reviewer gave me the suggestion, make this one another with a new figure. I just simplified this one, like the new figure. I think it's better. And next one is about the ND section, the 4.5. There was some typo and some editorial changes in the last 2 sentences. Actually, this is not really relevant to underspecified. So I just decided to remove it. This is okay. Thank you. And next one is the last one. Actually, this is about security section. The reviewer gave me the last second sentence. This one, actually, he gave me the suggestion. This sentence should go to the front in this section. So I just accepted one. And the second paragraph actually is not really clear because this is final version. So I just remove it. And the last section, there's the review give me some revise the text. Just I accept that the one, just I put his suggestion. Thank you. This is the end question and comment. Thank you. Okay. Yeah. Cool.
Okay, so there are no comments. Okay, thank you for the presentation.
Thanks so much.
So Pascal Thubert, Cisco. So we have, can you go try, please, next slide. So we have done some work over the last 10 years on fragments at 6LO. Initially, it started with a very simple fragmentation mechanism whereby you just cut a message in pieces and throw the pieces. But we would not discuss if there is any problem of flow control with those pieces, if there is any problem of interaction between the previous pieces as they get forwarded over the network, like hidden terminal issues between various fragments, things like that. And we did not even discuss how fragments could be forwarded without reassembly at every hop. So the assumption was fragments would be reassembled at every hop. So we looked at it in this working group and found that you could actually get a better result if you would streamline the forwarding of fragments. But there are rules in order to do that, unless otherwise you get interactions between the fragments and you lose a lot of them. So we ended up with one document in this group, and Karsten wrote another document, Delwig, where we explain how, without changing the formats in 4944, you can actually avoid reassembling the packet at every hop, but forward the fragment over a layer-3 path over multi-hops. So the technique is effectively documented in this minimal fragment draft. So minimal doesn't change the formats of RSC 4944. It just explains the rules that you must follow if you want to avoid some mistakes which would be prime. So it's mostly an internal operation by the node, how to perform the fragment forwarding correctly. Now we're still in a world where the fragments are sent once and for all, and you expect that all the fragments would be received on the other side. If they are not, there is no way for the sender to know about this, apart from timing out at the upper layer. Which means that if a fragment is lost, the receiver will wait till death with this buffer locked with a big message in it. So it's a big buffer, and you have to wait till a timeout of minutes before you can release that buffer. Meaning that, and that happened actually, that you run out of buffer for any normal non-fragmented traffic, and now your throughput goes down dramatically. So what we did for that is we looked at the problems of retransmitting individual fragments. And so for that, that's the third draft, the fragment recovery draft. And we also looked at questions like what kind of interval you need to place between packets to make sure, between fragments, to make sure that the next fragment does not interfere with the previous fragment. So there we go. These are this is the history of what we are doing. So 4944 is quite old now, but those two are just completing work group as Carlos has just told us. So the changes in minimal fragments, we had some comments. We had two great reviews by Yach and Georgios. Thank you, Georgios. And I don't see Yach in the room. I don't know if he's here. Oh, yes, Yach. Thank you, Yach. And then we got your review, Carles. So with this, we kind of removed some claims which were not too useful, like the size of the virtual recovery buffer, reassembly buffer, because it depends on implementation now. But we clarified the abstract content that we expect to find here. We added a section in the security section about the attacks against the VRB and what is the exposure. And the exposure is not that big because you don't keep much data for each individual fragment, right? So it's a very small data per fragment. So you can still be attacked in the middle of the network by throwing at you many fragments of faked fragments which appear to come from different datagrams for which you need to create a VRB. But it takes many of those packets before it starts representing a lot of memory. We improved the clarity of the text that says how you manage the VRBs, like when you create them, when you discard them. And yes, we clarified things which were not written correctly or not fully obvious. You only route on the first fragment. The operation that you do for forwarding fragment is create a form of MPLS state. You use the datagram tag as an MPLS label, and the first, really as it is, the first fragment is routed per the IP header, and you lay out the fragment as you go, the label as you go. And then the other fragments follow the label path, and you actually switch the datagram tag as if it was a label hop by hop. And that's how you avoid some collisions that we described in this group. So these are the changes for the fragment forwarding thing. The fragment recovery follows the same logic for the initial path that is created by the first fragment based on the IP address. What it does on top is provide a bitmap. Each bit in the bitmap of acknowledgement bitmap tells you about one individual fragment, so you can actually retry any particular fragment individually. So you've got rules on how you manage the intermediate VRBs, and you find that because you have this additional signaling, the management of the VRB can be better. For instance, you know when the receiver has fully received all the fragments, that's when you can destroy the VRB. You don't know that if you don't have acknowledgement, so it's an addition to the text that could exist in the normal fragment forwarding. So we discussed with the chair here, with the Shepherd, actually, Shepherd Hatton, whether that meant an update of the other spec or just an extension. And we found that it's not really updating the other draft because the methods we are adding come with the fact that we are adding something in the protocol as well. So we didn't write update, we wrote extend, and we did not indicate in the RFC header that we update minimal fragment with the recoverable one. Added definitions, clarify a number of things. We also added the IANA section. It was missing. Or it was there, it was empty. So thank you again for locating this one. So yes, now we have an IANA section, and that's part of what was published this morning. And that's your question now?
Hey, Pascal, no, not a question. I'm here. It's hard to find me, but yeah. So one of the things that we've identified, this is not like just a problem here. This updates thing is an issue for everybody in the IETF pretty much. So like we used the updates tag to mean different things at different times. So a few of us on the IESG have taken upon ourselves to write something to clarify this. And just to give you like a brief intro, right? Like it's going to be an individual draft coming out, right? Like it's probably today or tomorrow it'll be out. We want to replace the updates tag with something else. Okay, so right now the goals are like one of them is like, you know, it changes things or adds things. Like, so we want to separate these things out. So like what the update means is going to become clearer. Okay, that's really the goal. I think like by this time this like hits the IESG, we might at least have like an initial idea of like whether this is going to fly or not. But it's not probably going to be final. But I think at least like in the text, you could explain how something updates. That's like probably going to be the stopgap arrangement for going forward with this, right? So you just say, okay, this is what we do, because like you said, right? Like it's an extension point, so you decide what to say. But so one of the things is like, so if I started digging back a bit, right? Why do we have an updates tag in an RFC, right? So the thing is like the RFC that got updated, right? The only way it can become mutable to point to something that has more information is the updates tag. So I would rather be like liberal in assigning the tag. If you think it's relevant for somebody reading the updated RFC to read this, I would put in the updates tag. Okay?
That's the point. I thought it was not.
It's not. That's what I'm saying. So like, I'll rather be liberal in doing that right now until we go through this proper cleanup procedure. So just because like somebody's probably going to ask like somewhere down the line, right? Like, and I would rather be liberal here and then remove it if somebody says like, why does it do it? As long as you explain it, I think we're going to be okay.
Yes, and so we had that, and I guess this case is one you could have in your thought process as you define those new tags, because in this case, the minimal is still self-sufficient. The addition don't need to be known by somebody who does minimal for RFC 4944. This is a closed word that it's enough, and there is nothing to add to it.
Already thought of, yes.
Sorry?
It's already thought of. So that's why I just wait for the draft. It's probably be out today or tomorrow. So like it is like something that's a use case for like the new tags.
Okay, yeah. So, but you see the point, right? The update, if it was, does not actually need to be known by the reader of the other one, because the update comes with what comes with this draft itself, also self-sufficient. So that's why I went for not updating. Good. So yes, thank you very much to the shepherd for both documents, who happens to be Carlos here. And yes, the document is moving on, as you said. So we're all set for the int area review, I guess. And that's pretty much it for this one. Thank you, Forwarding fragments, as we go to the next slide, where is more complex than meets the eye, because if you just push the fragments bang, 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 and you operate your mesh on a single frequency, clearly the first fragment, as it progresses from the first to the second hop, well, for the second to the third hop, will collision on the second hop with the second fragment, which comes from the first hop to the second hop. It's like, because you think you forward it this way, actually, because the radio is broadcast, it also forwards the other way. And the two interfere. So you get immediately a hidden terminal, and the second hop loses the second packet, basically. So it's something that forces you to pace down your fragment. It's something you need to know. Now, if you operate on different channels, like you use TACH, for instance, you still need to pace a little bit down, because when the second fragment is sent, the receiver on the second hop must be open for receiving, meaning that it must already have sent the first fragment. So the sender of the second fragment must wait till the receiver of the first fragment has done transmitting. Right? So you still need to insert some time here, even if you don't have hidden terminal programs, because you need to be able to turn the receiver on the receiver. So it must have sent the first fragment. So there are a lot of non-obvious things like this. So there we go.
You get a break. There is a use case draft presentation, and then you come back for that.
Okay. Hi, my name is Yonggun Hong. I will present the 6LO applicability and use case document. So actually, this draft was not updated after last Prime meeting, but we have email discussion between the authors, and we have some rough consensus, rough conclusion how to improve and how to update this draft. So this time I will shortly describe the result of the email discussion. The first one is the author agreed to adjust the scope because the comment come from the last meeting. So we will narrow down and focus on, and we found that some section was not consistent between each section, so we make consistency between each section, and we are debating to determine the 6LO technology. The first one is LTMTC is removed already, but we are considering how about handling the IEEE 802.15.4 technology, because RFC 65668 already provide the 6LO band use cases, but in this draft, the typical deployment of the 6LO, that is the Python mesh and the YSUN. The two technology is a typical 6-row deployment scenario, and it is based on area 2.15.4 technology. And another technology is IEEE area 2.15.echo technology. I remember that it comes from the Samhita comment. Samhita suggests that IEEE area 2.15.echo is also related to 6-row, so it is better to include that technology. But now the draft is a little too big, so we must remove. It is not important section. So one of the technologies is IEEE area 2.15.echo technology. Comment?
Just to mention that 4E has been wrapped into 15.4, so it's just part of 15.4 now. The one you mentioned, WISE and Jupyter Mesh, are in the 4G family, where the PHY is actually sub-gig and you go long distance, whereas 4E was in the, well, it could be used for 4G, but it's an upper MAC technology, like TSCH, time-slotted channel wrapping, is part of the 4E amendment. But now it's all wrapped up into 15.4, so there's no reason to mention 4E anymore.
Okay, thank you. And the other conclusion is that we would remove the section 5.1 that title is the design space dimension for 6-row deployment. So RFC 65668, it includes the design space based on the 6-row PAN technology, but we identify another design space dimension for 6-row deployment because 6-row technology includes wire technology, for example, BACnet or PLC. So there will be a different design space dimension. But we found that each design space dimension is not related to each 6-row technology. So to narrow down this draft, we would like to remove the section 5.1. So if you have any comment or any questions, so let us know, then we will consider how to adjust the scope of this draft. Okay, that's all. Thank you.
Carlos Gomez, as a co-author, I think, well, if you go back to the previous slide, yeah, I think the last point is the clearest action that we can do. It doesn't hurt if we remove subsection 5.1 altogether. Then the one in the middle is a bit more tricky. There's the question of currently in the description of technologies, we have a subsection for 15.4e. The question might be, okay, should we have a subsection dedicated to 15.4? In general, perhaps yes. Also, Pascal just mentioned that now 4E, 4G are integrated anyway in 15.4, although that might open a bit the scope as well. So that's a little bit tricky.
Okay, then. So right now I have no answer to to your question. So okay, I think about how to handle that issue. Okay, then another question on comment.
So how do you want to, question to the authors, how do you want to progress? It was in work group last call. We didn't submit it back. We didn't get any comments. We didn't submit it to the ISG review. So how do you want to proceed? You want to revise the draft and go for another work group last call, or you want to gather some thoughts from the work group now to see if there is interest in actually progressing this draft and see if there is an archival value for this draft at this point? Okay,
let me answer. So my plan is to update this draft, and then we hope to ask a comment from the 6-row, and then we will ask the working group last call.
Okay.
That's all. Okay, thank you.
Pascal again.
So this is an update that I prepared not for this group actually, but for 6man. But then talking with the chairs, we thought relevant to give this group an update on it because it really builds on what we have produced in 6LO. and that now may continue its life at 6 man. So for those who did not follow the story, now is your chance to get it to kind of the full story of wireless ND. So actually the work really started with RFC 6775, which I should have written here. So RFC 6775 introduced the concept of a registration, which is how a host can tell the router, hey, I have this IP address, or I formed this IP address. Can I use it? Is it unique in the network, etc.? And the router, using a central registrar we call the 6LBR, is capable of saying, yes, this address is unique, you may use it, basically. And now the router is, and the 6LBR can protect the ownership of this address to this host. So that was the beginning of the story. With this interface, we mostly can do duplicate address detection, but there is no security mechanism to ensure that a bad guy will not try to register the same address with the same MAC address and steal the traffic and be able to source traffic on behalf of the other guys. So for good, willing guys, this is a DAD equivalent to what we have on wire. But for attacks, it's just as what we see on wire. It's possible to attack this and claim the traffic for somebody else. So that's 6775. 8505 updated this, changing a little bit the way we use link local address, making it simpler, and also changing which field advertise that. So it's mostly conceptually the same thing. In terms of exact format, it changes a bit. And then we added something which is important in some environments, which is a sequence counter. For instance, we refer to this draft 8505 in data center applications where VMs can move. And the fact that you have the sequence counter, and each time the VM moves, it declares itself to the router, then the routing infrastructure as a whole can always know which is the most recent location for this virtual machine. It's a problem we see on wireless. It's a problem we see in the data center. We want to know where everybody is, and we want to make sure that we know the latest point of attachment of that address. Right. So having this sequence counter is actually critical for getting this information tight. So that's 8505. And then there are two drafts which progressed pretty much in parallel to 8505. The first one is the Badman Router. So the Badman Router, and I will have slides on that, is really the ND proxy operation that goes with the registration. So if you think for a minute of what 802.11 is providing you at layer 2, in the infrastructure mode provides you with an emulation of a broadcast domain, so you can operate your IPv6 stack exactly, quote unquote, as if it was Ethernet. And to emulate the broadcast domain with multiple wireless nodes, which each have a different broadcast domain, they all agree that the broadcast domain of reference is that of the access point. Right? Meaning that if you want to send a broadcast from a station, what you actually do is send it to the AP, and the AP would broadcast it. So everybody who can receive this broadcast must be in the broadcast domain of the AP, or the APs if you have an extended service set. What we are doing with this registration and this Badman Router is we are pretty much doing the exact same thing at layer 3. And now if you wonder why .11 did the way they did, well, think for a minute about how a transpond proxy operates. You know, those learning bridges. What they do is when they don't know what where a MAC address is, they will just flood the network with a broadcast. And when the packet comes back from that MAC address, that they will orient the bridge and say, oh, that MAC address is on this port. If you wanted to do the same thing at layer 2 on Wi-Fi, you would end up broadcasting any new lookup for any MAC address. And from the wireless perspective, that's completely unacceptable because broadcast is actually expensive on .11. So from the start, the .11 designer said, hey, I can't have this reactive operation. I will be proactive. So part of what you do with an association process is you actually pre-establish a bridging state in the access point. So when there is a lookup, a broadcast, the access point already knows whether the MAC address is attached to it or not. So it will actually cancel the broadcast and it will not copy it on the wireless if there is nobody interested on the wireless side. Right. So basically, you avoid the cost of this lookup and the broadcast that's associated to it. What we do with 8505 and the Badman Router is we do the exact same thing, but at layer 3. 8505 becomes the association, and the Badman Router is this transparent bridge, but at layer 3. So when there is this broadcast happening, in NNS lookup, now the access point, the layer 3 access point, can recognize whether the IP address is already associated, registered to it. So it can know whether it's useful to just cancel the lookup or turn it into unicast or just reply on behalf. With the Badman Router, you can do all those operations. Right. So we've reached the same state with this method in IPv6 where you can avoid the cost of the lookup over the wireless network. The address protection draft, APND, is in that world the equivalent to CERN, to Secure ND. Secure ND is very complex because you're securing any to any NS lookup, basically, which means that you have to place your crypto between any peers. If you operate in a registration mode, you must think again like an AP. A station does not send a packet to another station in infrastructure mode. It sends the packet to the AP, and the AP sends it to the other station because you have to live within the broadcast domain of the access point. At layer 3, when we do the Badman Router and 8505, the prefixes are advertised as not on link. Because your desired operation is exactly the same thing. You want the packet to go to the router, the layer 3 access point, and the router forward the packet back to the destination station, right? So by protecting the ownership of the address at the router, using some crypto mechanism, proof of ownership, etc., we can provide the equivalent service of SAND without distributing all the SAN stack to every device. It's just between the device and the router. And it's quite easy to do because as you register the address for the first time, then you can give a token instead of a MAC address, it's now a crypto token, and you can use it for proof of ownership later. So if your IP address moves from a layer 3 IP to another layer 3 IP, the AP can challenge you for the ownership of this token, which is stored in the infrastructure. And so you can prove that you're still the guy who registered this address for the first time. First come, first serve. So we can actually deliver the savvy properties. We can do source address validation. I will only forward the packet if it comes from the rightful owner. And I will not let an attacker get an address that belongs to somebody else because he cannot prove the ownership. So that's pretty much what APND does. So with this, we were kind of done emulating, an infrastructure ESS at layer 3. So now we could start living, I would say, without all the layer 2 broadcast emulation that you have in infrastructure mode, which is good for new applications like OCB. But we still use the normal ND operation on the backbone. Meaning that even if we protect the wireless, we don't protect the wire. The wire is still the same as it was ever. So there is this new draft which we published like 6 months ago, unicast lookup. And this one actually extends the methods that we have developed for the wireless side onto the backbone, like on Ethernet. If you work on overlays and big fabrics, you're already used to the fact that if you want to establish a VXLAN between ingress and egress, you have to resolve the egress point for a given IP address, right? So there is this notion that there is this central database somewhere, a map server, map resolver of sort, which knows every IP address on the network and where it is, because you need to establish an overlay tunnel between the ingress and the egress. So it's nothing new for many of us who do those kind of networks. But there is no simple abstraction for a wireless phone or a PC to talk to the map server, map resolver. They don't talk Lisp, right? And so we are missing this simple interface that would allow any IP address to tell the map server, I'm here. So that when there is a lookup, instead of having to broadcast over all the fabric, you can actually just look on the map server, map resolver to know the MAC address and be done. And with this, you save all those broadcasts that ND is doing on your fabric. So that was something which just is a simple extension to what we have in wireless, but it's really not done for wireless. It's really done for wire. So that's one of those reasons why I tend to think that the work which I started as a 6LO document should be actually a 6-man document, right? And that's why I'm presenting those things, this presentation and the unicast lookup at 6-man tomorrow. So I wanted this section here of this presentation was to give them the story, so now they know where the unicast lookup comes from. But for people, I talk to in Cisco, it's more like I'm telling them, hey, what I'm after is a standard interface in neighbor discovery to populate the map server, so that the devices don't have to talk list, because they don't. Right. And so this new draft is actually something which is targeted to 6-man, to give them the whole story, to show them that in a world where the plain Ethernet is not the only case, where you have a lot of wireless with or without broadcast emulation at the layer 2, where you have data centers, overlays, etc., the methods that we defined in last century for a yellow cable can be slightly obsolete, and that we may want to actually refresh ND. And it's evolve or die, basically. Some people say, okay, let's just do point-to-point and be done with it, and ND becomes almost nothing. It becomes an LDP or whatever. Or you actually refresh it and modernize it so that you can still use it and build large subnets with it. I'm in favor of building large subnets. I'm in favor of, because we do it, we have subnets of thousands of devices in the field that we ship right now. We have large conferences, we have smart grid applications, we have a ton of applications where a large subnet is useful. At the same time, we want to avoid the broadcast on those large fabrics, which means that we want to route, which means that we want to take those processes that you're used to seeing in MAC layer emulation, like the infrastructure mode in .11, and you want to move that to layer 3 and use that state to route inside the fabric. So for those in this room who have been doing repo and those meshes, etc., it's no surprise that's what we do every day. But for people coming from a more traditional world of 6-man, it's more of a shock, because some people never wanted to hear about multi-link subnet. There is this idea that a subnet is a link and a link is a subnet. Some people don't even realize, oh, one is physical, the other one is logical. And actually, you could map the logical thing on bigger than a link or on smaller than a link. For people, because of Ethernet, they see that as pretty much the same thing anyway. It's not. And actually, this presentation after that is all about different subnet models. And applied to wireless, what is my link model and what is my subnet model? Because it's not obvious. It's not Ethernet. So that was a long introduction, but you told me I had time. Tomorrow I won't. So I hope that, well, I'm happy that you're here, because tomorrow I won't be able to say all those words. So basically, ND, the way it was designed was for point-to-point and transit link. It's written in big letter in the draft. And that's because it uses broadcast, uses layer 2 broadcast. Some people tell me, oh, it's multicast. I say, what joke is that? Because there is no such a thing as layer 2 multicast. Well, there is, nobody deployed it. And anyway, it's not meant, the one that the IEEE has produced is not meant to scale to 2 to the power of 24 bits. Right, so there's no such a thing as a layer 2 solicited not multicast. Don't dream. So when we, with our good faith, send packets to the multicast group, the first thing that the IEEE does is place the first bit of the MAC address to 1, and the thing gets broadcasted through the fabric. There is no layer 2 magic to solve the problem that we did not solve. We just pushed it over the fence, hoping that the IEEE would solve this for us. Never happened. Right. So Wi-Fi does a emulation of a transit link, and that's why IPv6 over Ethernet can be translated into IPv6 over Wi-Fi. But it has impacts because radios are not wires, in particular multicast. On the radio, there are a number of things which are kind of interesting, which happen when you send a multicast versus a unicast. When you send a multicast, you have to send it at the slowest speed possible because you want to reach everybody who is associated to you. Okay, it means that some packets can take 100 times the airspace of a unicast packet that could be sent much faster. Second thing is, when you do broadcast, you cannot beamform, right? You have to send it multi-directional, omnidirectional. Whereas when you do unicast, you can beamform and then multiplex, MIMO, multiple packets. So when I hear that doing P2P, doing broadcast over a P2P is like doing a unicast, unicast. It's wrong because the PHY won't do the same thing if you tell him it's a broadcast and if you tell him a unicast. Even if you aim at a single person and you have a logical P2P connection with that person, if you don't tell the PHY that it is a unicast, if it has the broadcast bit, it will tune the radio differently. It will be slower. It will be omnidirectional. Okay, so it's important to turn any packet you can into a unicast. Okay, so usually so far we've done MAC layer 2 emulation to make believe that you can do Ethernet. And really I started this draft when I started reviewing the IPv6 over OCB. OCB is this mode of .11 that's designed for cars where you don't have the infrastructure mode. You don't have ESS and BSS. You're naked. You're just like on 15.4, IPv6 over the PHY, meaning that the broadcast domain are those of the sender, not those of the access point, meaning that all of the assumptions that we made, that there is a single broadcast domain so we can do IPv6 ND the way it stands, all this is broken, doesn't work. Right, so that's all these long discussions for those who followed IPWave, but that was my knee-jerk reaction to the initial IPWave documents. Even if there is a MAC layer emulation of a transit domain of a full broadcast domain everybody is in, it hurts. It hurts because the broadcast is slow. It hurts because when there are so many broadcasts, your battery is rapidly depleted. I don't know if you found it, but I found that my phone goes depleted twice as fast at the IETF than at home. It's processing all those broadcasts. It's processing so many broadcasts that the phones usually have protective methods by which they filter a number of them. If they filter a number of them and one of them is important, well, it's not retried. Like if I do this DAD over my fabric, there is a good chance that the number of the phones will just filter it out because they keep 1 out of 5 or something like that. Well, the end result is my DAD operation will fail. So how come IPv6 seems to work? Because the duplication don't happen, right? You have to force a duplication in v6 to really see one. If you leave it to MAC address or random or or the RFCs we have from 6man, the chances of a duplication are so low that the user perspective of the service is always working. But in fact, the core operation that's behind it, that doesn't work. We tried it at the IETF. We found that on a big meeting like this, 1 DAD out of 5 discovers the duplication. It's completely useless. It works because the problem does not occur, not because we know how to solve it. Right. So having the infrastructure know the addresses of everybody in a registrar, map server, now we can really do the DAD, and we don't have to have the radios always sound to defend themselves because we have an infrastructure service for doing it. Okay. And there are a number of other mismatches actually. Oh, you tell me when I take too much time, right? But I think this is so interesting, right? I want to share with you. I want to make sure that you're on the right page on all those things because it doesn't meet the eye. I mean, it's something that you have to think quite through before you really get your mind on it. So there are a number of other mismatches with traditional ND. The first one is .11r fast roaming. Fast roaming expects that you can just get there and the infrastructure will always know where you are. At layer 3, that's probably true, right? Because you reassociate rapidly, but at layer 2. But at layer 3, when you have this, you snoop the protocols and you try to figure out where the latest location of a particular device is, and we're doing that today in this network. If the guy moves really rapidly with .11r, The messages that we send over the fabric to say, I've seen him here, I've seen him here, might arrive in disorder, meaning that the layer 3 infrastructure might think is here and actually is there. Now, if you use that for a VXLAN, then you lose all your packets because tunnels are not routed to the right place. So you better not run too fast. That's the first message. Second one is intermittent connectivity. If you want to save your battery, you don't receive all packets all the time. So how can you do that? How can you defend yourself? Because you're not even on to say, hey, that's my address. Another use case which came up more recently is the case that .11 calls fields. So it's the so-called Tokyo Station case. All the guys come out from the train at the same time, and they want to have instant connectivity, hundreds of people. So for that, the IEEE has been working very hard to make the association process very quick and massively scalable. But guess what? To get the IPv6 traffic through, it takes 1 to 10 seconds. And there is actually a draft at 6.9 by Jen Linkova, which just describes this particular phenomenon. Even if you do optimistic DAD, which saves you 1 second, you still may take up to 10, 15 seconds to get your first packet through. And there are a number of reasons for that. And one of them is the reactive nature of ND. Because when the router will see your address for the first time, instead of being able to forward the packet, it has to resolve the MAC address. So you're in the Tokyo station, you just join, you send a few packets to the Googles of the world to see what kind of connectivity you have. And the server somewhere in the infra starts responding to you. The router, the first time it sees one of those packets, it will punt it to software. The software will send an ND message, wait for NNS, wait for NNA. During that time, if more packets arrive, the packets will be dropped because the router wants to protect itself, right? And after the NA comes back, maybe one packet will be sent to the station, which will say, hey, I have a very limited connectivity on that network. Let me retry in 5 seconds. So you can put all the efforts you want at layer 2. If the layer 3 did not proactively set the ND cache on the router before the first packet comes from the infrastructure as a response, you're screwed, right? You can save 40 milliseconds or 100 milliseconds at the MAC layer. You lose 10 seconds at layer 3. That's kind of sad, right? So that's another miss from ND, because ND was designed at a time where doing some software operation on the fly on the received packet was okay. Right now, we do everything in silicon, and we certainly punting a packet to the software to do an ND resolution is something completely absurd. We're in a world where the routing protocols always, apart from money, pre-populate the silicon, the fib, before we even need it. But on the last hop, because of ND, right? So what we really want is to be able to pre-populate the ND cache before it's even needed, so we don't lose those 10 seconds plus. And we don't have all those attack vectors that we can have with ND. And visitor. Yeah. So now to get there, we need to think a little bit. The first thing we need to think of is what's my link model. What you have at the file level is this broadcast domain. Right? So you get Mr. A, which has a broadcast domain, and I can broadcast on this. And you've got Mr. B, which has this broadcast domain. Is that my IP link? Well, some people say it's my IP link. It's my broadcast domain. So quote unquote, I can talk to whoever is in my broadcast domain because I expect that to be reflexive, which is true or not true. It can be true if there is no interferer and we have the same antennas and we have the same power levels, etc. In our Wi-Fi infrastructure, we find that there is a ratio 1 to 10 between the quality of the signal in both directions, right? Even if the station adapts the power to that of the AP, which is supposed to do. The AP is supposed to say, hey, I'm sending to you at this power. The station is supposed to use the same power back. But actually, the antennas are not the same. Nothing is the same. And even the quality of the chain is not the same. So at the end of the day, you don't get the same signal. It's not really bidirectional. It's not reflexive. But it's mostly reflexive. What is not is transitive. So basically, you can build this link when two people are in each other's broadcast domain. So is that what you call the link? I tend to think that's what I want to call a link. Why? Because I want to form a link local address. And there is no point, no way to do that once and for all on a radio interface, which is always on. Say my OCB radio in my car, always on. Can I do that for an IP address in the morning and drive through the world? I mean, obviously, that does nothing, because who was in the range when I did it at 8 in the morning at home, and then I drive through town? If there is duplication, I could not detect it from home. What's the point? And I never turned on my interface. I never detected anything. When should I redo that? On the other hand, if you consider that your link is when you can actually talk, discover Mr. B and talk to him, and that the uniqueness of your link local has to be asserted only between those two. And that's right? If he does not know anybody called Pascal and I don't know anybody called Robert, I can call him Robert and I don't make a mistake, and he can call me Pascal. That's enough. As long as I have a single Robert around me, I can talk to Robert without any problem, without any duplication and misunderstanding. So the way we do it in 80505 is exactly like that. We say, you don't have to assert the uniqueness of your IP address once and for all. That doesn't work. You have to do it individually with every people you talk to. So the link layer address, the link local address, is not actually looked up on this central registrar, etc., for uniqueness. It's just between you and your first hop router. Never goes anywhere else. And you don't route them. But if you do a route over mesh, you don't route to link locals, right? Because it's one hop. So we really see the link as being this point-to-point thing. That actually, we build a P2P subnet if we like, and that's the minimal thing that we can do. Then we need to, this is kind of a physical reachability thing, right? It's your link. If you look at 82200, it kind of words what is an IP link as if it's a medium, right? A physical thing. Here we're already halfway to the logical thing. So it's even reading 80200, it's not very clear. What should the concept of a link be? Should it be my broadcast domain, or should it be this peer-to-peer, point-to-point connection? But then because of that and things like that, it makes a lot of more sense to consider it's the point-to-point connection. Now, should I live with only point-to-point subnets like some people want to do? Well, if you build a smart grid network with thousands of nodes, having to deploy thousands of prefixes for just two sensors talking to one another and relaying, that seems a bit absurd. You could do it. You have ample room in V6 if you want to deploy it this way. Now, the users don't want to deploy it this way. They want to say just this span is this prefix, and then you route inside it using Ripple. That's how we deploy those things. So it's still useful to build a more complex network. So the first case that we can think of is hub and spoke. This is the case of an RSU, a roadside unit, and you have two cars which are next to this roadside unit. And the roadside unit can actually provide connectivity to the world. So what you see in this model is that the roadside unit broadcast domain is exactly like that as an AP, right? You can say, oh, I can broadcast to whoever my hub can talk to. And then, or get the equivalent of a broadcast and make a subnet of it. If you say not on link, you get the exact same service at layer 3 than at layer 2. You go every time through the hub, and then you go to your destination. So the simple action of saying not on link gives you that. Now, what's more interesting is the prefixes, right? You can be on the same prefix as this guy because you never talk directly to him. You don't need to be in his broadcast domain because you don't do that, you don't do lookup. You don't do that because 8505 registers your address to the hub B, and the hub is responsible for telling this address is duplicate or not. So there is no that. You just register, and the registration succeeds, you're on. The registration fails because there is duplicate, you form a new address, you try again. But you never have to do that again. He's in charge for a lifetime. And now for lookup, you don't look up. You talk to your router, and he will care. Because he has a registration on the other side, he will know how to forward. So you see how 8505 actually solves the problem when you have hub and spoke connectivity at layer 2. So like I said, in OCB, you don't have a broadcast emulation at MAC layer. You have to do the same servers, but at layer 3. And that's exactly what 8505 does for you.
Pascal, quick time check. We are 25 minutes into this, and
okay.
We have unicast lookup to cover up.
Okay, so let me see. I will cover this more slide and be done with this presentation. So the last model that we see a lot, and that's how we build our mesh, our smart grid things, is this mesh here. So we still build this point-to-point connection, and then we route between them, and we use Ripple. So in this case here, all you need is just one hop forwarding. So you don't need routing. You need routing as soon as you've got 2 hop forwarding. Right? And that's when we actually play repo. And with 8505, what you do then is you need a central register we call a 6LBR, which comes from RFC 6775. And now you get uniqueness of your address. When you've got uniqueness of your address, you can inject it in the routing fabric and get to any place. The bottom line is you never broadcast. Right? At least at ND level. Now there is a last situation where actually your multi-link subnet is heterogeneous, meaning that you have a different quality of network in the backbone and in the wireless access. So in this case, it's just mapping, again, a Wi-Fi network, but this could be a full mesh. So in a Wi-Fi network, you have hub and spoke, the AP, the layer 3 AP, and all the stations, all the hosts. And you have this backbone. And the Badman Router here is doing proxy neighbor discovery. So when there is a lookup, the Badman Router having a state for spoke A will say, yes, it's here, turn the broadcast into unicast so it can respond. So that's just one of those things you can do. Right? If he's sleeping, and basically the Badman Router could reply on behalf of a sleeping proxy if there is like a DAD. So you can do all those sorts of operations. The key thing is on the backbone, it's still the good old ND. So you do broadcast or everything, it's just not propagated on the wireless. And that's when I will switch to the other presentation.
Do you want to ask the questions on what kind of help you need from this group if you want to pursue this in 6-man?
Well, from this group, it's just more like trying to get a sense that we're done with what we could do. And now we go to maintenance mode. If we go to maintenance mode, then it's probably 6-man. And it's question to the group, question to the AD. But it seems to me that there's kind of a logical transfer when the technology has been done in a group that the maintenance is not necessarily done in that group, but in 6-man, unless 6LO wants to keep the maintenance of it.
And what will be the implication on already published or to be published drafts that we have in 6LO?
Well, we turn them RFC here, right? Those things, we turn them RFC here, but then do we want to give, because what could happen to this is get generalized to more interface. That's a discussion which just happened on 6-man. Do we generalize that to more interfaces? It makes a lot of sense to do that, but then it would not be 6LO. So why don't we say, hey, it goes to 6-man, they maintain it, and they generalize it to more interfaces? That's one thing on the table.
Yeah, Suresh Krishnan. So not speaking as AD here, but as like someone who's interested in this topic. So there's a bunch of us who did like similar kind of work in 6-man before. So Eric Nordmark, Samita, who's sitting right behind here. So one of the things that has like not been addressed like very well, and it's very hard to address properly, is the backward compatibility with the stuff that's there currently. Okay, so if you have a network where there's like
there's a lot of text in Badman Router about it.
I understand.
Yes, okay.
Right? Like what I'm trying to say is like, to generalize something so like everybody uses this as the default ND is like a lot of work. Okay, so I'm not. You could think no, right? Like, that's kind of what we thought too. So like as like authors, and it just takes a lot of time. So I wouldn't assume that this will happen soon. So it could happen, right? Like, but I think it's going to take its time. So like, I think we'll have the conversation, like, how it's going to get maintained, but like the 6LO specs have to be maintained here by 6LO, at least until like 6LO exists, right? Like, and I think it's pretty far out before we can think of like closing 6LO. So I think let's do things one at a time. I think you have a good starting document for the discussions, and in this room we're gonna get the constraint node, like the 6LO kind of perspective, and then you're gonna see the perspective from people who are doing something completely different. Like this, like the DHCP-v6 discussion, right? Like you had this discussion, right? Like for people say, oh, I want to run DHCP-v6, like a random IAD lens, right? And so those kind of discussions will happen in 6-man, because like people have different views, and that's really the goal of 6-man, right? Is to bring all these perspectives together. So here, if you go into any of this, like I would call it like constraint node cluster working groups, like you'll find mostly support here, right? But like if you go to the wider community, there's people with like different operational models and different kind of constraints who might have other things to bring up. And I'm not saying it's possible or not to do. I'm just saying it's like don't think it's going to be a short-term thing, like this is going to get done. That's what I'm wanting you.
You know,
Thanks.
yeah, we were there, Sabita, Eric, myself, we are on the efficient ND effort, and yes, I know exactly what we went through. I was there. So I see what you're saying.
Thank you.
And so, yes, Sabita?
No, I said I don't want to repeat, but I agree with Suresh that you would have easier time in this working group than others.
Right, but if we want to extend it to other links, then we have to take it to 6 months. There's no, so it's just a matter.
At some point, yes.
So this is interesting discussion because initially it's for like maintaining the old drafts, and it makes a lot of sense to continue here. But when you have to port them to different links, or when you have to do new functions like this one in particular, that's when it becomes a lot less clear. So that's why it's interesting to see, you know, how every logic applies to whom. So unicast lookup is just new, right? It's just a personal submission at this moment. It was new at last IETF, so it's like 3-4 months old. What's it about? It's about scaling even your backbone infrastructure. It's about enabling overlay structures like VXLAN or NVO3, whatever you play as an overlay. I've been told, I never tried myself because I don't have enough PCs to try that, that there are limitations to what you can do with just ND on a backbone, even wired. And that's due to the broadcast storm that ND will cause. Because each time you have, mostly if those devices are wireless, so they come, they go, they join a different IP, you turn them to sleep, you start them over, they will form a new address. All this creates a background pressure of broadcast on your Wi-Fi. So that's one thing, but it also creates that pressure on the infrastructure itself, meaning that you have to refresh the mapping servers and all those things, you have to snoop the packets, and sometimes we do it right, sometimes we fail. Bottom line is all those broadcasts hurt. Mostly if you start distributing your layer 2 fabric over layer 3, like you have multiple sites with the same layer 2 domain, that hurts when you have all those broadcasts, right? And the bigger you build this thing, the more it hurts. So broadcast was okay on a single yellow wire. It's much, much less okay on a multi-site layer 2 domain. So scaling a network like this to tens of thousands of nodes is something that we want to build. It's not something that works easily with ND just because of this reactive broadcast operation. And like I said, modern topologies, they want this resolver to be able to just build the overlay in the first place. The way we do that today is we snoop the protocols. So we actually have to program the TCAM, intercept the packets in hardware, ND packets, recognize them, push them to software. We call that punt. So we punt to software. Now we analyze the packet. We do something like a reverse engineering of the protocol, try to figure out who is where based on snooping those packets. So we snoop ND, we snoop DHCP, we snoop actually data packets if the source is not known to us. So we can actually trigger like ND packets to see who's there. So we do all the sorts of games because we don't know who's where. And we need to know who's where to be able to enable our overlay. It's high time that there's a protocol that tells us precisely where every IP address is so we can have an overlay that works for all our customers. Right? That's what we want to build. We want to build a good overlay service, and it could span over multiple domains, multiple over layer 3, right? You span over your cloud over different places. For that, we need a registration protocol, and we need it on Ethernet. We don't need it only on wireless devices. And not only do we need a registration, but we need to centralize all this information so we can do lookup. Because what kills us today is all those lookups, which are broadcast over the whole fabric. So if you can have a central registrar that we do have, but that can be queried by any host through a standard interface, then it's a lot better. A host today will not talk Lisp. Our map server talks Lisp. Right, so unless we implement Lisp in every host, then we have this map server, but you don't know. So you will do the broadcast. So why don't we just extend ND a little bit so that using a simple NS lookup, instead of doing it broadcast, we do it unicast to the map server. For that, you need to locate the map server, big deal. And then you just ask him. If there was a registration for that address, he will tell you. If there was none, in a mixed environment, you will still need to do NS lookup. But at least you tried. And you see the sort of game you get is the more devices play by the new rule, the less broadcast there will be for everybody. It's a game theory thing. The more players, the more we win, right? Because the more lookups will be answered unicast, and there will be less broadcast for everybody. So by playing the game of registration, you actually help everybody else, not really yourself. Good. So that's what this unicast thing is all about. So you can do an NS directly to him, but if you're behind a wireless interface, for instance, and you already do the NS to your router, then the router will do it on your behalf. That's the model of 6775 and 8505. You register to your router, and the router goes to the central registrar, which is the 6LBR. So the bottom line is what we are doing is we are placing a 6LBR on the backbone. Up to now, the 6LBR was somewhere here, usually collocated with the Badman Router. Now we say, hey, why don't we share this thing for everybody, including the wired guys? So for us, it's mostly about displacing a function, but also adding this little API to do lookup. Because for now, it was mostly used for that. Now we do address resolution. And you see, the goal is to take a 6LO fabric, this 6LBR, and give it to 6 men. So now the question I asked to Suresh, earlier, becomes relevant again because the case has changed. So this is 6LO methods, but applied to really a 6-man case. So where should it happen? There. I have my answer. So this is now, for whoever this can interest, this is the FILS use case again, the Tokyo Station game that I talked about earlier. This is how things should work. If you do it this way, then you can have your traffic almost instantly enabled as you go in the station. So basically what the wireless guy does when he accesses the network is DNA. It tries to locate a router and tries to first unicast to his own router. Well, that won't work. So it will send a multicast to all routers. And the cool thing is it is a multicast, but remember at layer 2, it's first a unicast to the AP, right? And because we have a layer 3 AP, it will actually go all the way to layer 3. And what the AP will say, hey, oh, no, don't broadcast it. I can handle. So it will never be broadcasted on the layer 2. It will be absorbed by the layer 3 AP, which will actually answer by a unicast array. So in this phase here, you don't have a broadcast. That's the first thing you need to realize. There is no MAC layer broadcast on a wireless. Then there is this NS ERO, which is the registration itself. ERO is the address registration option. And that's when the 6 backbone router here will form the ND cache before there is any packet for it. So now the MAC address of the station here is known. If you're lucky with the new draft, you actually you get your registration to the 6LBR, which tells you, oh, it's unique. Okay, you've passed that. At this point, that is done. But if you're in a mixed environment where there are some nodes which register to the 6LBR and some which did not, which is your question earlier, you still have to run that. So this will mostly respond in an interesting manner if there is a duplicate. But if there is none, then if you're in mixed environment, you still need to do that. So it's a broadcast here, but you don't have to wait for the answer. Normally you should wait 1 second, but we have ODAD. So optimistic DAD is what I represented here. So you send an RS with no SLAO because you cannot, right? That's the RFC. And if the router doesn't have a neighbor cache for you, then it will try to respond unicast. If it tries to respond unicast, that means it will look you up. And that you can respond by ODAD. Okay, so with this little NS lookup, which is also broadcast, you respond with an NA, you being the backbone router, the proxy, right? And now the default router has a state for you. And now the packets can flow both directions. 1 second later, that times out. Who cares? I mean, the traffic has started for a long time. Okay, this is how you can make V6 work in a matter of split second. So that's pretty much what we are after. So we also changed the DARDAC because if you see this picture, in this case, the 6LN is not directly connected to the Ethernet. It's a wireless guy. So the request is actually done by the 6LBR on behalf. And the lookup could be that way as well. So we extended the DARDAC exchange, which is normally for DAD, so that you can also do lookup with it. Otherwise, it's Well, it's almost zero extension to what we already have. It's mostly placing it on the backbone. So I had to add a new value for the return code, say not found, which did not exist for that, obviously. And that's pretty much it. Voila.
Thank you, Pascal. So you want this work to be done at 6 months? So
I want nothing. I want this work to happen. I don't have any religion of where. It's just that. Well, Suresh knows better.
So we should still. I mean, we should first go to 6 months and see how it is received there. Okay.
So I'm presenting those two presentations tomorrow at 6 months, and you have 10 minutes to do it. What?
Now you know you need to shorten something.
Well, I already knew, like they sent me back my slides and say, well, give me 3. So that's a lot less, but at least I could give all this background and information. I hope it was useful to you guys.
Thank you. Brian?
Okay, this is sort of an experiment on my part. I'm working with Zhang Sheng and Li Guangpeng. At least that's my attempt at pronouncing their names, and I apologize for how bad it was on this. The original idea came from Sheng, actually, not from me. And it's called asymmetric IPv6 because it has to be called something. So what's the motivation for this? You know this, that physical MTU size and bit rate may be very small in edge deployments, at least, of very highly constrained nodes. Additionally, the edge router, the first top router, may be very constrained. And the thesis behind this work is that in a very constrained router, the traditional compression and decompression algorithms use resources that you don't want to use, and that sacrilege 128-bit addresses consume memory. They consume memory in ribs and fibs, and they consume memory in buffers and so on. So the approach is to tackle those two problems simultaneously. The fact that traditional compression and decompression takes time, and the fact that big addresses take memory. The way to approach it is to make the addresses shorter, obviously, inside the IPv6 packets. Do the routing based on shortened addresses, not to transmit any unnecessary bytes, and avoid the overhead of compression and decompression algorithms in the process of forwarding a packet through a router, right? How this would mix and play with other solutions is definitely for further study. I should say that right at the front, because otherwise Pascal will start bouncing up and down, I suspect. So the method is to, within a domain, there has to be a finite domain within which this applies, define an address length, we'll call it n, and all addresses inside the domain are assumed to have a common prefix of 128 minus n bits. So in other words, there is a prefix which everyone agrees on is the prefix that's relevant within that domain. And outside the domain, we're going to be using 128-bit addresses with that prefix stuck on the front to complete the address. So the ribs and fibs can use short addresses for intra-domain forwarding, and any forwarding to the outside world or from the outside world towards this domain will use the full length address. So there's going to be some slightly strange business going on in the router that sits between the domain and full length IP. Unnecessary header bytes simply missed out. That's sort of a fairly obvious thing to do. And to do all that, the idea is to use what we call flexible header encoding, so the headers are not in a fixed format, they're in a somewhat flexible format. And Pascal is beginning to jump up and down.
Laura is the co-author of page 138, so we look at each other.
Yeah, okay. Yeah. So, within the domain, the first thing you have to do is decide what the address length is. Everyone has to agree on that, obviously. It could be configured by the manufacturer, it could be configured by operators, could be configured by users, actually, or it's parameterized in some way, and a gateway between this domain and the rest of the world communicates the address length to everybody else, or it could even be negotiated. So that this is still completely open, right? Exactly how you would do that. This is getting a bit specific, and I must say, is Guangpeng in the room? Hope so. I didn't do this slide. This is a suggestion that to make this work, we could add a flag to the standard IPv6 RA, which says that if you receive this RA, you can use the asymmetric IPv6 mechanism, and the prefix would be a modified prefix information option to tell you what the prefix was and what its length was. And then when you're doing address configuration, if that bit is set in the RA, I don't even know if I'd need to go through these details. You can do that as homework. You know, it becomes algorithmically possible for a node to compute its address in a fairly obvious way. And all this needs to be reduced to precise language and algorithms which are not in the current draft, right? Because this thing is changing in front of your face as we speak. And a lot of what, you know, you probably have to execute some kind of duplicate address detection before you can bind the address. But it's all fairly intuitive, I think, once you know that that address length is communicated to you in the RA, as well as the prefix. Then what do you actually put on the wire? Well, this is where it gets a little bit strange. One way is to use a new dispatch value in 6LoWPAN terms. The other approach is to use this flexible header encoding concept, where the packet actually starts with a flexible header encoding octet, which has obviously 8 bits in it, which have various significance. And then, because 8 bits may not be quite enough, you've got another 4 bits you can use. They're normally called a version number. It's always contains 0110. So why not use those bits as well, since they're actually no use in an IPv6 packet? So that gives you basically 12 bits in which you can indicate which fields are actually present in the header. So this example, there's a payload length, there's a next header, standard IPv6 next header, there's a hop limit, and there's a truncated destination address, truncated because it is under the domain prefix, so you don't need to include the domain prefix bits. And there's no source address because, well, people know your source address anyway from your MAC address. Once you're in the ND cache, your source address is associated with your MAC address. Look it up backwards. Yeah, of course, you can't use this for the first packet because nobody knows who you are. And in the draft, you'll find the layout of those bits and how they work. For example, the version number bits, it's in small print at the bottom. If the version number bits say 0, you're going to be carrying full 128-bit addresses in the destination, but the source address is truncated to the domain-specific length, and so on. And it turns out we even got some reserved values among the bits, because there are quite a few of them. Yes?
Yes. Alors, Tota from IETF Atlantic. I'm working in LP1 in a compression mechanism that is called SHIC. And SHIC is not in the same area because it's on LP1 network, so you have a star topology and we don't need address, but these things looks to make the link between low-pan networks and LP1s, because if you look at what we have defined in SHIC, we have a rule ID that defines the compressed format we are sending on the network. And then we are able to compress either to suppress some of them or to reduce the size with the mechanisms that are inside the SHIC rule.
Yeah, I heard about SHIC about an hour ago, and I haven't read it yet. But, you know, obviously this is early stage work, and if we can swap ideas and combine ideas, that will be a good thing. Yeah.
Yeah, Suresh Krishnan. So no excuse for not knowing SHIC. Everybody had T-shirts for like the last few meetings. So, no Heidi had. I think like one issue I see right away with this header format is like the alignment. Like all the bit fields are like not aligned. So like the payload length, like the 16-bit field with no alignment, same with the hop limit. I think if you're coding in C, it's not going to be very fun.
Yeah. I agree they're not aligned, but if, you know, this stuff is going to go into custom ASICs, then the game's different anyway, right? So if you're coding in C, some of it's a bit of a nuisance, I agree.
Okay.
But that's not the whole universe. Shall I? Oh, go on.
I feel like if you prefer to wait for the end, I come back at the end.
Well, there's not much more, so...
I wait for
yeah. Okay, this basically points out that the gateway between the domain and the rest of the world has to expand or contract addresses. You know, so if something arrives with a short address, it has to go out. It has to expand it to the full length address, and in the opposite direction coming in. But within inside the domain, you could communicate entirely using the shortened addresses, and in some cases with no source address, because that's implicit anyway. Yeah. There is theoretically an option that you could even shorten the addresses of external nodes by giving them a sort of proxy address internally. So that's, you know, another name for doing that is NAT, right? So obviously some of the traditional NAT problems would arise, but you're not obliged necessarily to use 128-bit addresses for outside nodes either. I think that's all I want to say about that slide. So that basically is all we wanted to say. There is this idea, we don't know who might want to work with us. We might be told it's all rubbish. Sheng is sitting at the back, so he can add his comments if he likes. Sheng, why don't you go to a microphone so you can help to answer the questions?
Hello, Guangpeng from Huawei, one of the authors of this draft. The main requirement from the very simple scenarios like a supermarket and the endpoint device are very simple and resource limited. So they just want to talk with each other, and maybe only with addresses, source and destination. So here the draft will solve the problem of how to address the endpoints and with no other functions. So IPv6 may be so heavy for this scenario. And I also know there are many perfect compression approaches like a SHIC and 6LoWPAN, but which may need to compress and decompress when communicated with each other. Here we just want to mostly reuse the IPv6 schema to solve the common problems. Thank you.
Yeah, we perhaps need to say more about use cases in the draft, actually.
Pascal Thubert. First thing is, yes, I just sent you this email, like telling you there is also 8138 to look at. 8138 has pretty much the concepts that you elaborate in mind. Actually, the problems that you're talking about, this is the right place to talk about it first. I mean, this is the right group because that's kind of the problem we've been looking at for 10 plus years. Right? So you're in the right place. And obviously, we did a lot and thought in many different directions. Now, when I just look at what you propose, first, there is this argument that compression is difficult. Well, the 6LoWPAN compression, difficult is a hard word, but I think saying that what you do is not a compression is actually a fallacy because you're doing pretty much the same thing as we are doing.
Yeah.
Right. So saying I'm not doing compression, you're doing compression, so my stuff is good, your stuff is not good. You're doing the same thing as we are doing. Now, the other argument, which is very interesting, is can I process the packet in that format? Like, can I route in that format? And can I receive the packet in that format? And, well, it's true. That's really important. And if you look at 8138 when you have time, and it's that thick, you realize that it's completely designed to be forwarded in the compressed format, to be operated in the compressed format. You never want to look at the original format. But it's equivalent. And just like it's the same, I mean, we share so much the goals. I mean, we did not want to have to transmit address in the full, we want to transmit them in a compressed fashion. Mm-hmm. Now, we did not want to enforce a same compression for all addresses in the domain, like for now you're doing. We can actually decide address per address how much we compress it. And we can actually place a source route header, which is very important in low-power devices, right? Sometimes you can't have state to route over multiple hops. So we also thought about, how can I write this packet as you want to write it such a way that it's very easy to forward. And like you said, the source is not important. What's important is like the destination. But if you do source routing, it's not just the first stop destination, it's just all the other destinations. And then you start thinking, hey, do I like the swap that I have to do between the routing header and the IP? Oh, no, let's remove that. Anyway, I don't care about keeping the whole chain, so why don't I put it in the beginning and cut stuff? So you realize that the kind of thing that started this draft, this is the kind of thinking we've had for like 10 years. And we went very, very far in that direction, actually. So I really want to work with you on understanding, is there a gap that we have not covered yet? So far, I've not seen that gap in your presentation. I think we're covered already to do what you want to achieve. In particular, you don't have to expand anything. You can work with the compressed formats. If your code understands the compressed format, why ever work in the uncompressed format?
Within the domain, yes, I agree.
Yes, within the question is... and then at the border router, yes, you have to do the compression, decompression. And like I said, I think it's a fallacy to call it an adaptation layer. You can, but it is, but it does compression, decompression. That's what it does. You've shown me two formats. One is smaller than the other. I call that a compression, right? Saying I avoid the process, and now you can just say, oh, my compression is simpler than yours. Well, we can discuss a beauty contest if you like, and we can improve 6LoWPAN if you prove us that we can do better. But we are in the very same family, we have very same goals, and we've pretty much achieved what you claim you're after. And for some things, I think we did it better. Like the size of the compressed thing, we are much more elastic. Now, for other things, maybe you have a better approach, and we can improve what we did. But you're not starting from scratch. We've had a lot of experience on that.
Next.
Carlos Gomez, thank you for bringing this work and for the presentation. As a participant, I'm curious. I don't know if maybe you have any sort of evaluation, some kind of quantification of the effect of minimizing or avoiding decompression, because I understand that avoiding decompression is one of the main points in your proposal. So I don't know if you have any sort of evaluation.
The people who could answer that are standing behind you.
Yeah, exactly. Actually,
this is Sheng.
Sheng, Huawei. Actually, the motivation we had is what we saw in 6LoWPAN. There is, compression and decompression, and it has to do every hop when it goes to layer 3 routing. But what we want to do is we had this address be able to build up the routing table within the domain without any compression and decompression. So in that way, actually, within the domain, there's only necessary address as limited as possible. Yeah, so that's for every node and for every package.
Pascal again. That's an interesting discussion because I like the behavior as you describe it, right? It's a behavior thing, it's not a format thing. And so right now I've seen formats, right? I claim that with the formats we have in 6LoWPAN, you can do exactly that. You can build your routing table in such a way that if you know, for instance, that you're in a REPL geodag, just to give you an example, because we built for that, and you know what's the size of the bits which are always common, then actually we have a context that we distribute through arrays that tells us what this context is, and we can actually remove that from everything. And in all the packets, you see only the rest. And now having a routing table which contains only that rest, it's completely an implementation. It's not visible from the outside. So you can really build it. We never said don't do that. It's just completely opaque to the outside. We've processed the packet. We can process the packet in a compressed format, and we don't, mostly with 8138, right? We just snip the first of the destination addresses, which is just like a routing header, just snip the first and forward. It's very simple. And if your routing table contains 8 bytes per address because you know the first 8 are common, that's fine. It's your implementation. So I claim we do that already. Now we could describe, that operation inside the box. The formats we have already enable it.
Mm-hmm. Okay.
Pascal, I could agree on what you claim the 6LoWPAN actually could do that, but actually that's the problem because the 6LoWPAN actually describe a framework could have many different subgroup of it, but to do that, each of them, the 6LoWPAN framework become complicated. So you can say what we're doing is a simplified version of 6LoWPAN. That's fine. I don't care. What I care is those constraint node could do it in the simplest way and save the energy for them. Right?
To be proven. No, not necessarily right. I mean, think for a second about the LWIG work that we did, that Carsten did for fragments. It was enabled by 6LoWPAN, but nobody wrote that you could have this behavior. So those documents on fragmentation, fragment forwarding, and the LWIG draft were useful. They will be RFC'd, but they did not need to change the formats. So what I'm saying is, if you could have a simplest behavior or a subset of the behavior by documenting that behavior, that's orthogonal to providing new formats. What I'm claiming so far, I'm not saying that we have documented the behavior that you talk about. And I did not say it's not useful to document it. I said you don't necessarily want to change the formats to get it because the formats we have allow it. So far, for what I've seen, right? Maybe in the details you show me that we missed something, and then you can elaborate on the formats you have. Look at 8138 as a starting point about the formats we have.
Yeah, we will. Yeah, you had one more question?
We have one more presentation to go, so that should be the last. I think we'll have to cut the queue.
Okay, so we have a side meeting Wednesday morning, 8:30 in Notre Dame, which is somewhere close. And we're discussing another draft as well, but if anybody has time at 8:30 on Wednesday morning, please come along. That would be very helpful.
Okay, I have the last comments. Here we want to argue which is the best formatting here. Instead, we want to say the compression may be stateful or non-stateful. And for stateful compression, the context is very important. Here, we think if we can standardize the context in the drafts, and then on running environment, we don't need that anymore. So we assume we can configure the length of the address when deploy the devices. Okay.
Can we request you to add a section in the draft to compare and contrast with the existing solutions and come back to 6LO?
Yes. For example, if we want to adopt a chic schema to do the formatting, and we can standardize which rules can be used for the asymmetric IP. Okay.
Pascal, I think the line is cut off, isn't it? Yeah. Or I just wanted to make like one point there. I think that's absolutely important that like the motivation for this is there. I think Brian like touched on it a bit. I think it's best written down in the draft, like why, and I fully support that. Like, you know, just writing down like why the current mechanisms are not sufficient. Okay. And also, in addition to that, I would like to see some of the requirements, because like you mentioned about like, you know, what is needed and like what's the use cases. I think Brian touched on it too. I think if it all goes in the draft, it's really good because people can actually make their determination themselves. Yeah.
Okay. Thank you. So Charlie is up next. He's presenting it. He's a remote presenter. So should he raise his hand to make? Could you join the queue, Charlie? Perhaps that would help us make you the presenter. Charlie, if you're in Meet Echo, there is a button to enter the queue. It's in the right corner.
Right corner.
Left. Okay.
Hello? Oh, good. Okay. Well, this is my first time
doing
this remote presentation. So let's see. I don't exactly know how it all goes. Do I do something to advance to the next slide? Okay. Well, go ahead.
You could just tell us. We'll plan it. Yeah.
So this is a deadline draft is about a new routing header type that carries information about to enable better delivery of packets that have delivery constraint delivery constraints. So that means that the devices that receive a packet with this header in it can make the right decision about scheduling their delivery to the next hop. Requirement and the assumption is that the network devices are time synchronized, and there's a little bit of specification to show how to handle different time zones. This is basically the idea of the draft, and it's been pretty much the same for a long time. Next slide, please. So this shows the history of the draft. I guess I don't really need to go through this too much. This is, we have another revision out recently, and that's where the focus of this discussion this morning will be. So let's see. Yeah, I don't think there's anything else that needs to be said about this slide. Next slide, please. The current status is that there's been quite many reviews and it's under IESG evaluation. And we had some discuss points, particularly about how it is that the new routing header could be abused by nodes wishing to take unfair advantage by claiming that their data needs to be treated with a short delivery time. And so there was some text added to the security associations to basically say, yes, this is a problem, but if you have devices in your network that can take some unfair advantage, then you probably have other problems as well. And so the assumption is that the devices are deployed in a way that allows them to cooperate effectively. Next slide, please. Yeah. Yeah. Hi.
Charlie, this is Suresh here. Hey, yeah. So one of the things I haven't seen is a response to Alyssa's discuss at all. So I saw you responded to Roman and Magnus, but I haven't seen a response at all. So I was kind of like trying to match up to the responses, but I didn't see any. So if you made changes, like I think it'll be good, like just put the changes into a response to her discuss,
Okay,
and then
well,
we can
I
start
thought that we
discussing
had
it
provided
in the
responses
IESG.
to all the discussed points, and maybe I'll just go back and check. I mean, I'm quite sure that the email went out. Whether or not it went out specifically tagged as a response to this discuss from, for instance, Alyssa, I don't know that, so I'll check to be sure.
Okay, that's fine. So just let me know, Charlie, right? Point me to it, and then I'll take it from there, right? Like, so I think the mail was sent like 15th of May or something. Alyssa's, I think it's the day before the telechat. Just go look it up, and if you think it's addressed, just like respond to the
good.
email,
Well, I'll
or
do
just send
that,
me a private note, and
presumably
I'll
today or
make sure I
tomorrow.
follow up this week.
You bet. Okay, next
Perfect.
slide,
Thanks, Charlie.
please. So as mentioned, there was a new material in the security considerations about the expected deployment scenarios. Well, actually, that was a separate request for us to describe how, in our expectation, the document would be implemented and deployed for what purposes. So there was some discussion about that. And with a lot of corrections made, it's amazing how many little places there are to make mistakes. And also, there was a pretty good amount of material added, several paragraphs to describe really how to go about using shorter time ranges so that you don't always have to use the maximum number of bits to specify what the deadline time is or the origination time delta. And so I think that hopefully this revision of the slide set has a page about that, which I'll describe a little bit more. But several people noticed that there was basically some arithmetic errors, and all those things were corrected, and as well as for clarifications. And believe it or not, there was one place where the order of the description of the fields didn't match the order of the fields as they were laid out in the routing header. So all those things were done, and I think that we have responded to all the comments and discusses and suggestions for improvement. Next slide, please. So this basically is the same as it's been, except for slight corrections. So for example, if you look under the deadline time value, the minimum amount of deadline time is shown as, the minimum, what can I say? If you're going to send the packet, you have a deadline time. So the minimum DTL, the deadline time length, is 0, which means that you can have one hex digit. And so that shows that and then the maximum number then is 16 hex digits. So the deadline time can be specified in a small number of bits, or it can use the whole 64 bits. The origination time delta is to be subtracted from the deadline time, and that can be anywhere from 0 to 28 bits, because since it's only a 3-bit field, then you can only go up to 7, and 7 times 4 bits is 28 bits. Next slide, please. Oh.
Carsten Bormann, the last line of the slide should say OTD,
Carmen?
not
Yes.
OTL,
Hi.
talking about little errors.
Okay. Well,
it's saying OTL where it should say OTD.
If you have...
Just in case you copied that over from your draft.
Well, I didn't actually copy it, and due to circumstances, I didn't see these slides till today. So let's see. This was... Are you saying this was copied over from the previous presentation, or... I'm sorry, I didn't quite get that. But anyway, there was one more slide in the corrected presentation set that shows how Wraparound works. And I guess I'm not going to have a chance to present that last slide here. But if I can describe it verbally, what the effect of it is to, if you look at your synchronized timeline, maybe you can say it starts from 0 and goes to infinity, or at least what the maximum time is. Then if you want to have a shorter number of bits to represent the deadline time, maybe your length of the deadline time field is one extra, so that would make 2 hex digits, which gives you from 0 to 256. And basically what I tried to describe in the draft was how choosing a time interval of length 256 effectively slices up your entire timeline up into 256 time unit intervals, and then there's some wraparound description from that. So that was intended to be a lot clearer than the previous description in that section. And maybe this verbal account isn't very clear, but hopefully the new section will be much clearer. And I guess that's all I have to present.
Okay, is there any comment from the working group on the updates on this draft?
Thank you, Charlie. So we will look forward to the response to Alisa's discuss and then take it forward from there.
You know, I'm sad to say that there's a lot of
no questions in the room
there with you, so I'm not able to understand what you're saying.
Basically, we said that there were no questions in the room. So the next step is the response to Alisa and continuing from there.
Well, I have to apologize for not being able to understand that. It's very boomy. And if you send me email, I promise to respond immediately. and
yes, we've closed the door. Perhaps it's better now. Basically, we were saying that there were no questions in the room, and we expect the response to Alisa's email.
We did post a response,
and then we can continue from there.
To answer the list and discuss, and I will verify and make it more clear that that happened, and that I'll be able to do that within the next day. All right. Thanks a lot. my first time here on the remote.
Okay, thank you very much.
Bye-bye.
Thank you. Okay, so it's time to close the session. Thanks everyone, and see you all in Singapore.